This is Knowledge Engineering with Semantic Web Technologies, and this is Lecture 3, Ontologies and Logic. Today, we want to do a short recapitulation of first-order logic. Okay, so let's remember, last time we talked about propositional logic. In propositional logic, we had a rather flat world, so this changes with first-order logic. So what is different? In first-order logic, we can also make assumptions about sets of things. So for that, we have a new connective, which is called a quantifier. And we have a universal quantifier and an existential quantifier. So what does this do? An existential quantification, with that, you are able to make an assumption about an unknown individual. It means you do not have to name it. You make an assumption about the existence of something. You say something exists within a set of things. And on the other hand, with a universal quantifier, you can say an assumption holds for each and every individual within a domain you are looking in. So this is universal quantification and existential quantification. So this is new in first-order logic. What else? Just have a look at the syntax first. So we have the same operators, the same logical connectives as in propositional logic. Then we have variables. Why do we need variables? Okay, so if we make assumptions with the help of quantifiers, of course, we need variables because we say, okay, we make an assumption about an element within a set who or which has certain properties. And this, of course, usually you're using a variable that you can quantify over. Then you have functions like in propositional logic, and of course, you can also define the arity of the function. And besides functions, you also have relations, which are also called predicates. So here you see a small example of a typical first-order logic formula. So how do I form valid sentences or valid assumptions in first-order logic? So still first-order logic syntax. So what we do now first is we start with the correct formulation of so-called terms. And terms, they consist of variable, constants, and functions. So like you see here, so first example is a function f over the variable x, or you can have a function g over two arguments. First one is a constant, second one is a function of a variable, and so on and so on. So you see you have many possibilities to formulate correct terms. So with these terms, the next you try to construct so-called atoms. So by this, you're going to connect terms with the help of relations. So you see here a few examples of that. So here you have a relation p over a function f of x, for example, or you have here the relation q over a function s of a and over a function g of, and here you have two arguments. One is a constant a, and the second one again is a function over a variable, and so on and so on. So you see you have many possibilities here to create so-called correct atoms. But of course, you can also connect these atoms then with logical connectors and with quantifiers, and then you end up in a correct formulation of a formula over atoms, operators, and quantifiers, which might look, for example, like that one, where you, for example, quantify over all variables, which are here referred to as pixels, who have certain or have to fulfill certain constraints or conditions which are given further on. So this would be a correct formulation of a formula. Usually when you do this, if you are in doubt which comes first, just use brackets. So everybody should use brackets. And of course, all variables that you are using here within your first-order logic formula should be quantified. So this is also very, very important. So in propositional logic, of course, you don't need quantifiers. But if you want to state something like in propositional logic, this, of course, would hold for, let's say, all individuals that you make an assumption about. So therefore, everything can, of course, be quantified with a universal quantifier. Okay, so all variables should be quantified. And then you're going to make so-called well-formed logical formulas in first-order logic. Okay, let's have a look at a few formulas and how they translate into natural language, which somehow gives us something like an intentional semantics of these formulas. So here first we try to formulate all kids love ice cream. So what does it mean? So for all variable x it holds that if X is a child, then this child loves ice cream. Yeah, pretty straightforward. Let's look at the next one. The father of a person is a male parent. So how do I formulate that in first order logic? So for all variables X and all variables Y, it holds that if X is the father of Y, then and only then X is a male and X is a parent of Y. So you see, this reads also quite simply. Next thing, there are one or more interesting lectures, which means there exist, of course, one or more interesting lectures. Of course, I also hope that you consider this one as an interesting lecture. So, how does this read in first order logic? There exists a variable X for which holds X is a lecture and X at the same time is interesting. Okay, one more example. Here we have something, the relation is neighbor is symmetric. So this, in first order logic, would mean for all variables X and Y, it holds that if X is a neighbor of Y, then it also holds that Y is a neighbor of X. Of course, this means is neighbor is symmetric. But you have to beware. So these two especially are important for us. If we want to make assumptions here, for example, about all kids love ice cream, or if we want to say there exist interesting lectures. I will show you why you have to take care for that. So let's have a look at the difference here. So first we want to somehow formulate or represent all kids love ice cream. So the first one is the correct one. So it means for all variables X, it holds that if X is a child, then it loves ice cream. Which means, of course, if X is not a kid, of course it could be possible that X loves ice cream. So yeah, you see that. The other one would mean in blue, if you formulate it like that one, for all X, it holds that X is a child and X loves ice cream. So if you connect it via a conjunction, this would mean that all the individuals within your universe of consideration, they all are kids and they all love ice cream. So there is nothing which is not a kid and does not love ice cream. Is this really what you want to express? I guess not. And of course, you can prove this also again with the help of the truth tables of the connectors that you are considering. The other way around, let's have a look at this existential quantification example. So there are one or more interesting lectures. First one is the correct one. There exists an X for which holds X is a lecture and at the same time X is interesting, which means the things we address here must have both of the properties we specify here. If we would specify that with an implication, then we would have there exists an X for which if X is a lecture, then X is interesting. This would mean that if X is not a lecture, nevertheless the entire expression would compute true. And this is not necessarily what we have in mind. You know, if X is not a lecture, we can imply anything. So you see this because of the truth table. And this is not what we had in mind if we want to say they are one or more interesting lectures. So you see, you have to take care when you use quantifiers in the translation of natural language to first order logic and vice versa. So keep this in mind. We will do this again, of course, in the exercises. So this leads us to the so-called semantics of first order logic. And of course, here again, we're also considering a model theoretic semantics. Model theoretic semantics, you remember that we try to express the interpretation or the semantics of this logic, which is nothing else but a language, with the help of a simplified model. Okay, so let's have a look at here. So first, what we have to do is we have to define a domain of discourse, what things we are talking about. And then, of course, all the constant symbols that we are using have to be mapped to elements of D. So usually consider the domain D as a set of things, and then, of course, the individuals within that set. These are the constant symbols, and of course also I can map function symbols to this set or to functions which can be represented among the individuals of that set, and also likewise relations. And then, of course, assertions will also become element of D, of our domain of discourse. Also then the relation symbols with arguments will become true or false. And the logical connectives and quantifiers are treated likewise. So this, of course, is only an informal definition of first-order logic semantics. You can look this up in the material in detail. We want to have a look at the famous penguin example, where I further on explain you a little bit about semantics of first-order logic. So maybe you know that example already. So we are here considering a penguin who thinks about being a penguin, and he says penguins are black and white, and also some old TV shows are black and white. Therefore, yeah, some penguins are old TV shows. Of course, we know this doesn't make sense. So yeah, let's have a look why it is that way. Okay, so first of all, we can of course translate the natural language assumption of the penguin into first-order logic, which then will come up to something like that. So, for example, here we consider all variables x, where we say, okay, if x is a penguin, then x is black and white. And we connect this, of course, with the assumption that there exist some old TV shows who are also black and white. So some TV shows are black and white. There exists also an individual or variable x, for which holds that x is a TV show and nevertheless in the same time black and white. And from that, we imply that there exists, of course, a variable x for which it likewise holds that x is a penguin and x is an old TV show. Is this really possible? Yeah. To do this, of course, you can try to refute that. So for that, we have to find an interpretation for which this assumption doesn't hold. So let's try it in the following way. So first we set up a domain, and in our domain we have two individuals, we have two elements A and B. The nice thing here is if you want to translate the first-order logic formula, we do not have to consider any constants. There are no constants, and there also are no function symbols in there. So what we can do here, simply we have relations or predicates over variables, and of course these are substituted then by these two constants or elements A and B. So what we want to show is the formula is refutable, which means it's not in tautology, so it does not hold in every case. Of course it does not hold in every case. We know this from our everyday life. But to show that it doesn't hold, we have to find one example, one interpretation, where exactly this assumption computes to false. Okay. And it's quite simple because this is an implication, and we know an implication computes to false if the first part of the implication is true and the second part of the implication is false. Okay, so we have to find somehow, or we have to find an interpretation where simply the first part is true. So let's say for the individual A, it states that A is a penguin and therefore A is black and white. And we can say that, B is another individual for which it holds that B is an old TV show and also B is black and white. For the other side, or for the second part of the implication, we simply say that here the relation penguin for the old TV show computes to false, and we also can say that the relation old TV show, or the predicate old TV show for the penguin A computes to false. And if we assume these assignments to the predicates, then of course the entire formula computes to false. And then we have shown that this is not in tautology. So the formula with the interpretation I that we have given here computes to false, which means the formula cannot be entailed via this interpretation. So this was the penguin example so far. Let's additionally, in the end, have a short look at a few more properties of first-order logic. So first, logical entailment. So for that, we need a few more definitions. First, let's consider a theory. A theory is nothing else but a set of logical formulas in first-order logic. And then we define what a model is. A model is quite simple. So a model is an interpretation I of T, of this theory, if and exactly only if for all formulas G in T it holds that the interpretation is true. So I is an interpretation which is true, and all interpretations which are true are a model. So this is quite simple interpretation. Then a formula F is a logical consequence of the theory T if all models of T, of course, are also models of F, which means to prove that F really is a logical consequence of T, we have to take into account possibly all possible interpretation, which might make it rather complicated. But we will see how to deal with that. So then we write F can be entailed by T, by the theory T, which means F is a logical consequence of T. On the other hand, two formulas, F and G, they are called logically equivalent simply if you can entail G from F or you can entail F from G. So you must be able to make both entailments, only then they are logically equivalent. And you can write F is equivalent to G. So you might have wondered what a theory really is. So for us, usually we have already heard about the term knowledge base. So a theory is nothing else but a knowledge base. So you can treat these terms likewise. They are synonym in that sense. Then 2 or 3 more properties of first-order logic. First one, first-order logic is monotonous. So there is a monotony property, which says that if the knowledge base grows, all previously possible entailments still hold. And you can also express this, of course, in a formal way. You can say if S and T are theories and S is a subset of T, then of course it holds that all of the formulas which can be entailed from S are a subset of all of the formulas which can be entailed from T. And T, of course, it's larger than S, and S was, you remember that, a subset of T. So this means if the knowledge base grows, so with T grows, it's getting larger, then all previously possible entailments still hold. On the other hand, also first-order logic is compact, which means for each entailment made from a theory, a finite subset of the theory still is sufficient to make this entailment. So first-order logic is compact. But the most important property here is first-order logic is so-called semi-decidable. So what does that mean? First of all, first-order logic is not decidable. There does not exist an algorithm which always stops to prove whether F can be entailed from T or F cannot be entailed from T. So it's not decidable, but on the other hand, it's semi-decidable, which means then, for example, we have a logical consequence, so F can be entailed by T, and this can always be proven in a finite time, but not necessarily its opposite. So it cannot be proven in a finite time for all that F does not is not implied or is not a logical consequence of T. So this means semi-decidability. This is a bad property, of course, and this, of course, is also one of the reasons why first-order logic not necessarily is really the best possible tool for knowledge representation for our terms. And we are still looking for something which is a little bit smaller, not quite as heavy as first-order logic, but nevertheless expressive or sufficiently expressive for our purposes. Okay, so in the next part of the lecture, we want to apply what we have learned in the realm of mechanized reasoning. So first of all, I give you some rationale why it's important, this mechanized reasoning, and then we will have a first algorithm to do that, and this is the so-called tableau algorithm.